Dear students, today we will discuss about the model questions of Polytechnic of heat topic. Okay, we will start with the heat topic first. Now see the first question, which of the following is a warming process? Okay, and here the given options are evaporation, condensation, boiling, and all of this is given there. As given, it is about warming process, whereas warming process means where we are having the rise of temperature takes place. Okay. As we are seeing about this warming process, as given in the first option, it is about evaporation is there. See, we know that evaporation, okay, evaporation is a process where here there is a change of state takes place from, in case of this evaporation, it is going from liquid form to gaseous form, that is. Whenever in this case of evaporation, it is not like in the case of boiling. Evaporation takes place at any of the temperature you can take. So, that is why in case of evaporation, what happens there is, as the molecules which are moving on the surface, okay, of a substance like a liquid like water you can take, any other liquids you take, they collide each other and there is a transformation of energy takes place between the molecules. During this transformation of these energy there from one particle to another particle during the collision, they exchange their heat energies, then so that some of the molecules which are present at the surface, there is an increase in its energy takes place, so that because of taking that more energy here, they start converting their state from solid, from liquid to gas, that is. That process we call that as evaporation. But we know that in that evaporation process, what happens there is, as the molecules present inside the liquid, okay, those are of losing their energies, they are supplying they are giving their energies to the molecules which are changing their state. So, that is why as the energy of the molecules inside the liquid decreases, then what happens there is gradually decrease in the temperature levels takes place. So, that is why evaporation actually that is a cooling process, that is. So, that is why that is not a warming process. Then when you go to the second option, which is of condensation, if you take, condensation is a reverse process of evaporation we have, of which it takes place at any temperature here, that the substance or the molecules which are in the, we are taking gaseous state are converting into the liquid state here. Best example for that is in that winter season we will see the water molecules which are present, water vapor particles which are present in the air, because of due to that less in temperature in the surroundings, okay, they convert they are changing their state from gas to the liquid, they are converting their state from gas to the liquid on any of the surfaces here. So, that whenever this happens, what happens there is, it is giving the heat energy to the surroundings and it is forming on any of the surface which is a cold surface you can take. Best example for that is, we can take, if you are taking out any of the cold drinking water, or let us say for example, if you are taking from refrigerator any cool drink bottle here, around that cool drink bottle we will observe a small water droplets are forming here. That is because of due to, as that is a cold substance, that is here in the air, in humidity we are having that water vapor which is present in the air, that is converting its state from gas to the liquid and it is forming around that cool drink bottle, so that it converts into water droplets, that is. Then during this process taking place, that heat energy actually it is that heat energy it is giving out to the surroundings and it is forming on that surface here, so that all the heat energy actually it is giving to the surroundings here. So, as the heat energy is given to the surroundings, gradually that slowly that surroundings is slowly heating up, that is. Okay. As it is of heating up here, gradually there is a rise of temperature takes place. That is why in case of condensation process, we are having a chance there is a level of rise in temperature takes place. So, that is why condensation process is a warming process, that is. Whereas, in case of boiling, boiling takes place at gradually when you are supplying the heat, there is a rise in temperature takes place. So, that what happens there is that molecules they are converting their state, but at a constant temperature. But not in case of this condensation, we do not have a constant temperature here. So, that is why here condensation process only we are considering that as a warming process. So, evaporation that is a wrong process, whereas for our question condensation is correct. Condensation is a warming process, that is. Okay. Condensation is a warming process. Now, the next question is here the second one, melting is a process in which solid phase changes to. Okay. The options given are A, liquid phase, B, liquid at constant temperature, C given gaseous phase, and D given liquid at any temperature, that is. Here given that about melting process, that is. So, when we are taking about this melting is a process where here a solid, it is converting into a liquid state, means liquid phase, that is. So, solid phase converting into liquid phase, but this solid to liquid phase conversion here takes place only at a particular temperature, that is. That temperature only we call that as melting point, or it is also called as fusion point, melting point or fusion point, that is. In case of, for example, if you are taking for the case of ice, which is a solid phase, during the melting it converts into water, which is a liquid phase, that is. This process of melting of ice takes place only at 0 degrees Celsius. At normal temperature and pressure, if you take, actually it takes place at a standard pressure here. If you are taking that fusion point or the melting point for ice, it is about 0 degrees Celsius takes place. So, as the melting process, it takes place only at a constant temperature, as we seen in the given options, that option A given, that is of liquid phase there, and option B given at liquid phase at a constant temperature is given. So, the option is going to be the second one is correct, of which here we are having the second option, that converting from liquid here at a constant temperature, that is. Now, we will see the third question, that is reverse process of condensation is. Okay. Options given are option A freezing, option B melting, and option C evaporation, and option D boiling is given. So, here given it is about condensation process, reverse process they are asking. Condensation, earlier we seen that condensation is a process taking place as there is a change of phase taking place from liquid to the gas and gas to liquid here. Okay. So, during this condensation process, what happens there is the molecules which are present in the gaseous state, those are actually here changing their phase from gas to liquid. At any temperature it can take place. The same process in reverse, which is about that liquid, it is converting into the case of gas, of which that is nothing but evaporation takes place. That is nothing but evaporation. But here we are taking at any temperature, we are taking. Okay. Actually, condensation process, if you see, as in case of condensation process, this condensation process takes place, of which here that gas, it is converting into liquid form, that is a gaseous phase, it is converting into liquid at any temperature we are taking. Whereas the reverse process, then reverse of that means here you are taking that liquid, it is converting into gas, that is. Okay. That liquid, it is converting into the gaseous phase. Best example you can take in case of vapor, of which vapor particles, and it is converting into water, that is, and in reverse process, that is of water here, actually it is converting into vapor state, that is. The best example for this condensation is, as we seen in the previous questions there about that cool drink bottle, around that we are forming the water droplets, of which we call that as dew, that is. Now, here as the reverse of condensation process, which is about conversion of liquid to the gas here, okay, that is nothing but this evaporation process. So, of the given options they are given, okay, so evaporation is the correct one here. So, the correct answer for this third one, which is reverse process of condensation, is evaporation, which is option C is given, which is of evaporation, that is. Okay. Then if you go to the next question, which is of fourth one, when the temperature of water rises, the rate of evaporation. Here given that when the temperature of the water rises, so the rate of evaporation taking place, it is options given are A increases, B decreases, option C given remains the same, whereas option D given we cannot say. So, means here it is about again evaporation process. Now, whenever if you are increasing the temperature here, gradually what happens there is the kinetic energy of the molecules is increasing here, because we know that the average kinetic energy is directly proportional to the temperature of the molecules here. Okay. As the temperature gradually increases, the kinetic energy of the molecules also gradually increases. Once if you are having more and more kinetic energy is increasing, more and more kinetic energy is there, then the molecules are moving more velocity there, so that the number of collision takes place also gradually increases. As the number of collisions are increasing, there is a chance of more transfer of energy from one molecule to another molecule on the surface here. So that when there is a transfer of energy taking place is more here, then gradually what happens there is the rate of evaporation also gradually increases, which means that more number of molecules actually they are increasing their energies there, so that they can transform it from liquid to the gaseous state, that is. So that's why as the average kinetic energy is increasing, which means that the temperature levels are more here, that's why here the rate of evaporation process also taking place is increasing here. Okay, well, so for the fourth one, when the temperature of the water rises here, the rate of evaporation is increasing. So the correct answer is option A, that is. Okay. Now when come to the next one, which is of fifth one, if you are taking, when ice melts, its a temperature. Okay. Options given are option A decreases, option B increases, and option C remains the same, whereas D given cannot say that is. So here given that when ice starts melting, when there is a case of melting takes place, then melting process is nothing but, in case of melting, here solid it is converting into liquid state at constant temperature, that is at a constant temperature. That constant temperature only we call that as melting point. So as the melting takes place here, melting takes place only at the melting point here, or it is also called as fusion point, and melting another process name is fusion process, that is. This melting takes place for ice at 0 degrees Celsius, that is. Okay. Of the given options, which is given one, in case of that melting takes place at a constant temperature is given there. Okay. Whereas if you see our options again, it is given that is of decreasing and increasing there, remains the same there, and cannot say is there. So which means in this case at a remains same. So during the process of melting, there is no change of temperature takes place, which means that the kinetic energy of the molecules are not changing. All the heat energy supplied is utilized only for change of state. No energy is utilized for changing its kinetic energy here. So that's why no rise or fall in temperature takes place. So that's why the option is C, which is remains same. Then if you see the next question, which is of sixth one, evaporation is a process taking place at, options given are at high temperature, second B low temperature, C any temperature, and option D above boiling point. Okay. Now this is another process we have called evaporation process. See, evaporation process, as we know that evaporation is about the change of phase, okay, from liquid to gaseous to a phase, that is liquid to the gas. But this evaporation takes place need not to take at boiling point. Most of the cases actually, if you want to convert from liquid to the gas there, we have to increase the temperature of the body up to its boiling point. Whereas evaporation is a special case where here there is no need to raise the body temperature up to its boiling point. Actually here at any temperature you can take, at any temperature, here that liquid it is converting into gas. That process only we call that as evaporation process. Okay. So that's why if you see the given options there, in the given options we are having that evaporation process taking place at any temperature, which is option C is correct. Okay. Now when come to the case of next one, which is of seventh one, when we cool a gas below its condensation point, the kinetic energy of the molecules, see that question again there, when we cool a gas below its condensation point, the kinetic energy of the molecules, options given are increasing, B given decreasing, C given remains same, and option D given cannot say. So here again it is about condensation point. Remember, condensation it is taking place, which is a warming process, which is taking place here converting from gas to the liquid state, that is. As it is converting from gas to the liquid state here, Now we are taking, in this case, that condensation we are taking at a particular temperature we are taking. The kinetic energy of the molecules we are taking here. As it is of kinetic energy of the molecules decides the temperature, because the average kinetic energy is directly proportional to the temperature, that is directly proportional to the temperature, that is. Okay. Now, as condensation process, if you see, condensation process actually that is a warming process, that is. As the condensation process, it is a warming process here. Gradually it gives out all the heat energy to the surroundings, and those molecules lose their energy and they are coming onto the surface here. Like we see in case of that cool drink bottle or any of the surface here you can take, like windshields you can take here. During winter season morning we will see on the leaves we will see the small water droplets are present. Those water droplets actually, when they are in the vapor state, they are losing their energy and they are converting into the liquid state here. So that what happens there is the molecules are losing their energy. As the molecules are losing their energy, that is why the kinetic energy of that also decreases, that is. So here in the given options there, increases there, decreases there, remains the same there, cannot say there. So the answer is going to be decreases here, because the kinetic energy of the molecules is decreasing, that is. Now come to the case of 8th bit. If you see, the temperature of the body is directly proportional to, okay, given options are density, B potential energy, C kinetic energy, and option D none of the above here. So here given options are about the density there, potential energy there, kinetic energy here, and we are discussing about the temperature here. And we know that kinetic energy, now only we discuss that average kinetic energy and temperature both are related directly proportional to each other. As the movement of the molecules is more, if you have, so that what happens there is the exchange of heat takes place there, so that gradually the temperature is more. So that is why here the average kinetic energy of the molecules is directly proportional to the temperature we have. So that is why as in the given options there, we are having that kinetic energy is the correct one here, of which here we are having density there, B potential energy there, C kinetic energy there. So option C is the correct one. Now come to the next one, which is of 9th one. If you see, the internal energy of a system is, options given are option A vibration energy, B given potential energy, C given kinetic energy, and option D given all of these. So now this one, it is about internal energy here. Now internal energy is nothing but the energy present which is inside that substance or inside the body, that is internal energy. Actually this internal energy we are having different forms we have. For example, we are having the potential energy is also the internal energy here, because potential energy is nothing but the arrangement of molecules we are having, the energy possessed due to their positions here inside that substance, that gives you the potential energy, that is. And in that internal energy only we are having even kinetic energy also present. Again actually this kinetic energy we are having total two types we have. One is of in terms of linear and another one in terms of rotational we have, or vibration also you can take, okay, potential energy and kinetic energy. And third one we are having vibrational energy is present, okay, which is of vibration energy is there. Now actually this vibration energy is nothing but during this bond formation here we are having those molecules, they are vibrating in their mean position only. So that energy only we call that as vibrational energy, that is, okay. So inside that body we are having all the three types of energies are present, which means the potential energy is there, the kinetic energy is there, as well as the vibration energy is also present. So that is why of the given question there, the internal energy possess all the types of energies which are potential energies, kinetic energies, and vibrational energy also present. So that is why as the three correct options we have, A is correct, B is correct, and C is correct. That is why the option becomes all of these, that is, okay. Now when come to the next one, which is of the Celsius unit of heat is. Now the Celsius unit of heat we are having given options are joule is there, B calorie is there, C joule per gram is given, and option D given calorie per gram. then actually we know that heat, it is a form of energy, that is, heat is a form of energy which causes the sensation of hotness or coldness of a body, that is. As heat, it is a form of energy, and we know that energy, its SI system, it is of joule we have, okay. Whereas in case of CGS system, if you take, that is of calorie, that is, and MKS if you see, that is we are having kilocalories, that is, okay. SI system, it is of joule, CGS is calories, and MKS system, that is of kilocalories we have, okay. Now, as it is about unit of the energy here and is given in the question there, it is about CGS system. So, that is why the option becomes CGS system, which is calories is correct one, of which in the given options joule, calorie, joule per gram and calorie per gram, option B is correct. The numerical is given there. The temperature of a liquid is 70 degrees Celsius made with 100 ml of one liquid at 90 degrees Celsius and another liquid at 60 degrees Celsius. So, means that after mixing both the liquids here, 70 degrees Celsius we have with 100 ml of liquid at 90 degrees Celsius and another liquid at 60 degrees Celsius. The quantity of the second liquid mixed we have to find here, okay. Now, if you see that, given that mixed temperature there, of which after mixing the final temperature or the resultant temperature is given as 70 degrees Celsius, and also given that we are having the 100 ml of first liquid here, okay, 100 ml of first liquid, okay, liquid 1 we are having 100 ml is there, which is of 90 degrees Celsius is given. Whereas, second liquid, it is given that at 60 degrees Celsius, that is. The second liquid, its mass is not given, but given that it is of 60 degrees Celsius, that is. Okay. Now, after mixing both the liquids here, we are getting the temperature at 70 degrees Celsius. We will go to the next question, 12th question, that is. Okay. Now, as 12th question given, some hot water was added to 3 times its mass of the cold water at 10 degrees Celsius and the resultant temperature was found to be 20 degrees Celsius. What was the temperature of hot water mixed, that we have to find here, okay. As given that, it is given there, here 2 liquids are mixed here, so that first liquid, that first case water we are taking M, whereas another water we are taking 3 times that one, okay. Now, here after mixing that, we are getting that the final temperature is going to be 20 degrees Celsius, okay. The final temperature here, it is given 20 degrees Celsius, okay. This 3 times mixed water, actually it is mixed with the cold water at a 10 degrees Celsius, that is, okay. Some hot water it is mixed, we do not know how much is that hot water, but this one cold water we are having 3 times the mass of the hot water is given there, and the final temperature we got is 10 degrees Celsius, whereas that 3m, that cold water, it is at given 10 degrees Celsius, that is, okay. As the final temperature is 20 degrees Celsius here, if you are taking the hot body and the cold body here, we do not know the temperature of the hot body here and we are taking for the case of cold body. Now, hot body temperature, as we do not know, let it be that is TH, and the final cold body temperature is given 10 degrees Celsius. Then after mixing that hot water and cold water, actually we are getting one final temperature, that is, and that temperature is given 20 degrees Celsius, that is. So, cold body, that is increasing its temperature to 20 degrees Celsius, whereas hot body, it is decreasing its temperature to 10 degrees Celsius. Here masses are given, this is hot body, it is of having mass m, cold body it is having the mass 3m, that is, okay. Then if you are considering the formula here, the hot body here, according to the principle of calorimetry, whatever the heat energy we are taking for the case of hot body, during that mixing here, it loses its energy. Whatever the heat energy it is lost by the hot body, it is equal to the amount of heat energy gained by the cold body here. Amount of heat energy loss is equal to amount of heat energy gained by the cold body here. Then according to the formula, we know that Q is equal to Sm delta T for the case of hot body and Sm delta T for the case of cold body here. Okay. Then if you are taking the specific heat of hot body, which is our water, if you are taking, its specific heat capacity is 1 calorie per gram degree Celsius. So that's why the specific heat of water, which is 1 calorie per gram degree Celsius, and mass of that we don't know, let it be that is m only, and delta T, change of temperature. Actually initially it is at very high temperature, now it is decreased to 20 degrees Celsius. So that's why the change becomes Th minus 20, that is. And when come to the case of cold body, here again the specific heat, which is about, again we are taking for the case of water, which is 1 calorie per gram degree Celsius, that is. Whereas mass given that is 3 times the hot body temperature, that is, and change of temperature actually it is increased from 10 degrees Celsius to 20 degrees Celsius. So that's why here the change is 10, that is. So then this 1 calorie per gram degree Celsius, 1 calorie per gram degree Celsius get cancelled, and we are having m of Th minus 20 is equal to 3m of 10, that is. Okay. Then here that m get cancelled, finally we will get Th minus 20 is equal to 3 into 10, that is of 30, that is. Then the hot body temperature Th becomes 30 plus 20, which is 50 degrees Celsius. This is the answer. Okay. So the final temperature, that hot body temperature, finally it becomes 50 degree Celsius. Now if you see the next question, which is 13th one, a piece of iron of mass 2 kg has a thermal capacity of 966 joules per degree Celsius. Okay. Then the question is, how much heat is needed to warm it by 15 degrees Celsius, that is. Okay. Now, as the question, it is about given thermal capacity there, thermal capacity, or it is also called heat capacity, that is thermal capacity, represent with C. Now, this thermal capacity C, it is equal to m into S. Actually, if you see the definition here for thermal capacity is nothing but the amount of heat energy required by the whole mass of the substance to raise its temperature by 1 degree Celsius. Okay. So, see that the amount of heat energy required by the whole mass of the substance to raise its temperature by 1 degree Celsius, that only we call that as thermal capacity, where thermal capacity C is equal to Q by delta T, that is. Okay. That is its formula. But we know that Q is equal to Sm delta T here. So, as we also know that then S is equal to Q by M delta T, that is. If you compare these two, actually you will get then C is equal to, here only Q by delta T is C, but S is equal to Q by M delta T we have. So, that only thing extra quantity we are having, that is mass you are taking, because specific heat it is about the unit mass, whereas thermal capacity it is about the whole mass of the substance. So, that is why here the thermal capacity C becomes m into S, that is. And as in the given question there, it is about the amount of heat energy required. So, which is Q is equal to S into m into delta T, that is. Okay. Now, as the Q is equal to Sm delta T here, that C value already given that. So, that C is equal to given one is 996 joule per degree Celsius is given there. Okay, of which it is given 966 joule per degree Celsius. Then if you substitute that C is equal to, which is S into M, that is, if you substitute in that our equation there, then Q becomes, that is of 966 into change of temperature we have, which is given is 15 degrees Celsius there, of which required is 15 degrees Celsius, that is. So, we got, if you multiply that Q is equal to Sm delta T, which is, as Sm value we already know that given is 966 joule per degree Celsius into the raise in the temperature we need is 15 degrees Celsius. So, that is why here S into M, which is 966 into delta T, which is 15, that is 15 degrees Celsius, that is. Then 966 into 15 we will get 14,490 joules. So, the thermal capacity required, the amount of heat energy required for this case, it is about Q is equal to 14,490 joules. That is our answer. Of which that 14th one, if you see, calculate the amount of heat released when 5 grams of water at 20 degrees Celsius is changed into ice at 0 degrees Celsius and given specific heat of water is 4.2 joule per gram degree Celsius and specific latent heat of fusion of ice is given 336 joule per gram, that is here amount of heat energy required when 5 grams of water at 20 degrees Celsius is changed to ice we are taking. Okay. Then if you are taking 5 grams of water, okay, which is 5 grams of water at 20 degrees Celsius if you are taking, and we need to convert this 20 degrees Celsius of water, we have to convert that into ice. Okay. Ice at 0 degrees Celsius we have to take. Okay. So, 5 grams of water at 20 degrees Celsius, we have to convert that into ice which is at 0 degrees Celsius. But if you see here, there is a change of state takes place because water which is a liquid phase and whereas ice that is about solid phase here. This conversion of liquid to solid, that only we call that as freezing. We call that as freezing. As there is a change of state takes place, there are no temperature changes occurs. And freezing or melting, any of that actually it takes at its melting point or freezing point, which is in case of water that is 0 degrees Celsius, that is. Okay. So, means at first we need to bring down the temperature of the water from 20 degrees Celsius to 0 degrees Celsius. Means first we are converting 5 grams of water, okay, at 20 degrees Celsius. As the freezing point of water is at 0 degrees Celsius, first it is to take out the heat energy here, so that the temperature of the water becomes 0 degrees Celsius. 5 grams of water at 0 degrees Celsius. Let us suppose the amount of heat energy given out during this period, let it be that is Q1 is the heat. Now, as if you find the Q1 here, then Q1 is equal to, which is, as there is a no change of state here, water and water you are only taking, only the temperature changes. 20 degrees Celsius is becoming 0 degrees Celsius, that is. Then as there is a change of temperature takes place, then Q1 is equal to Sm delta T, whereas specific heat is already given 4.2 joule per caloric degree calories, that is gram degree Celsius, that is. As it is of 4.2 joule per gram degree Celsius, 4.2 joule is nothing but equal to 1 calorie, that is. So, which is 1 calorie per gram degree Celsius, whereas mass given which is of 5 grams, that is 5 grams, and change of temperature from 20 to 0 degrees Celsius. So, that is why here change in temperature becomes 20, that grams get cancelled, and here the amount of heat energy which is of 5 into 20, which is 100 calories of heat energy it gives out here. But here at this point, now water we are getting at 5 grams of water at 0 degrees Celsius is now available here. That 5 grams of water at 0 degrees Celsius, now it is becoming, okay, which is 5 grams of ice at 0 degrees Celsius. Now it is ready, because as the temperature is at 0 degrees Celsius, which is nothing but the freezing point of ice, that is. So, that we can get here that water it can convert to the ice. Change of phase takes place at this point. Okay. And we know that during the change of state, then the formula becomes Q is equal to M into L, where L means the latent heat capacity, that is, and it is given that the latent heat capacity of ice, which is given as 336 joules gram per degree Celsius, 336 calorie per degree Celsius is given there, whereas the 336 joule per degree Celsius is nothing but equal to 80 calories, that is. Okay. Now, you are taking that mass as mass given there, which is of 5, and latent heat of fusion, which is if you convert that into calorie per gram, it becomes 80 calories per gram, that is. Okay. That grams get cancelled, and again 5 into 80, which is of 400 calories, that is. Okay. So, first to convert from 5 grams of water at 20 degrees Celsius to 0 degrees Celsius, the amount of heat energy required is 100 calories, and if you want to convert again from water at 0 degrees Celsius to 5 grams of ice at 0 degrees Celsius, the second case the amount of heat energy given out is 400 calories. So, the total amount of heat energy required Q is equal to Q1 plus Q2, that is, which is 100 plus 400, that is, which is of 500 calories is the amount of heat energy required to convert complete 5 grams of water at 20 degrees Celsius to ice at 0 degrees Celsius. Okay. So, answer is 500 calories. Now, if you see the next one, which is 15th one, given that a vessel of negligible heat capacity contains 60 grams of ice in it at 0 degrees Celsius and 8 grams of steam at 100 degrees Celsius is passed into the ice to melt it. Then find the final temperature of the contents of the vessel, and given the values are there, specific latent heat capacity of a fusion of ice is 336 joule per gram degree Celsius given per gram given there, and specific heat capacity of water given 4.2 joule per gram degree Celsius. So, the given question, it is about ice at 0 degrees Celsius and 8 grams of water is given there. So, given that cold body which is ice, our cold body is ice which is of 60 grams is given, okay, whereas hot body which is steam which is given 8 grams is given there. Okay. So, that ice which is of 60 grams given, that is of at 0 degrees Celsius is given, this is 0 degrees Celsius, and steam actually it is at 100 degrees Celsius is given. And when both are mixed, actually here steam, we are having the latent heat capacity for the steam, it is about 540 calories per gram, that we know. But if you supply the heat energy to that ice there, actually it is about, it changes its state there from solid to the liquid, melting takes place, that is. And here the freezing point, already ice, it is at its melting point which is of 0 degrees Celsius, and this is steam which is giving you the heat energy of 8 grams here at 0 degrees, at 100 degrees Celsius is present. Then if you take the hot body and cold body, the maximum amount of heat energy that is required for melting of ice which is 60 grams is here Q is equal to, if you are taking the hot body and cold body there first. Our hot body is nothing but the steam which is 8 grams is there at 100 degrees Celsius, and cold body which is ice there which is of 0 degrees Celsius, that is. Okay. Now, here that 100 degrees Celsius which is the hot body having more temperature, and cold body is the ice which is at 0 degrees Celsius, of which we have to find the final temperature. But see, if you see, if steam is giving out the heat energy here, then what happens there is, now slowly it is converting into liquid, that is, which is, we have to take the change of state which is m into L, that is latent heat of vaporization, that is, plus here after change of state takes place there, after it is converting into the water there, slowly it decreases its temperature there, which means S into m into delta T, that is. Okay. Now, all that heat energy here, it is of for a hot body, it is equal to, for the case of cold body which is ice, on observing that heat energy here, actually it slowly starts raising its temperature. Before that, first it starts melting. As melting takes place, then m into latent heat of fusion comes here, m into L, plus again there is a change in the temperature takes place for the water which is coming from that ice. So, that is for the steam case, this is for the case of ice case, that is. Okay. As the mass given for the steam which is of 8 grams is given, and latent heat of vaporization is 540 calories per gram, plus and Sm delta T for that which is specific heat capacity of water is 1, its mass given there which is of 8 grams, and change of temperature from 100 it is decreasing to, let us suppose the final temperature is T, that is. This is all for the case of steam we are taking. And whereas in case of that cold body, if you are taking for the case of ice, its mass is given 60 and the latent heat of fusion is 80, plus the specific heat capacity here which is for the case after converting into water which is 1, and its mass which is of 60, and change of temperature for that from 0 it is increased to T. So, that is why the final temperature becomes T here. So, that is why change of temperature becomes T minus 0, that is. Then if you take 8 into 40 here which is of 4320 plus 8 into 100 800, okay, minus 8T is equal to 60 into 80 which is 4800 plus 60T, that is. Okay. What we need is we have to find the temperature here. Okay. Then if you find the temperature, then 4320 plus 800, which is 5120, and bring this 4800 this side is equal to 80 going that side becomes plus 80 plus 60t, that is. Okay. Then 5120 minus 4800, it becomes 320 is equal to 60 plus 80, which is of 68t, that is. Okay. Then T becomes, T is equal to 320 by 68, that is. So, as T is equal to 320 by 68, then if you calculate that, we are getting 4.70. Okay. So, that is the final temperature here. But if you observe 60 grams of ice here melting to 0 here, and 8 grams of steam, it is converting into water here. So, that is why the final composition, as it is a mixture of both ice and steam here, finally we are getting ice plus steam, which is 60 grams plus 8 grams. The total composition, it becomes 68 grams, that is 68 grams of water at 4.7 degrees Celsius we are getting. Okay. This is the final answer we got. 68 grams of water at 4.7 degrees Celsius, that is the final mixture we are getting on mixing ice plus steam. If you see the next question there, which is 16th one, if you see, a hot solid of mass 60 grams at 100 degrees Celsius is placed in 100 grams of water at 18 degrees Celsius. The final steady temperature recorded is 20 degrees Celsius. Then find the specific heat capacity of the solid given there. See, in this case, it is given that this hot body, it is at 100 degrees Celsius, whereas cold body, which is water, given that, which is of 100 grams there at 18 degrees Celsius is given. See, already the mixing temperature is already given, which is of 20 degrees Celsius, that is. Then what we have to find is the specific heat capacity of here. For the case of that solid, we have to find. Okay. Then hot body, it is of solid is given there. For that hot body, okay, for that solid, the temperature is given 100 degrees Celsius, whereas cold body, which is of the water, which is of given 18 degrees Celsius, and also given that the final temperature is 20 degrees Celsius, that is. Okay. The final temperature given is 20 degrees Celsius. Then if you see for the case of hot body, which is the solid, okay, now here the amount of heat energy lost by that hot body according to the principle, it is equal to amount of heat energy gained by the water here, because water temperature, it is at 18 degrees Celsius is given there. Then if you are taking for the case of hot body, its hot body mass is 60 grams is given there. So, as Q is equal to S m delta T, this is for hot body, and for the cold body, that is of S m delta T, which is for cold body, that is. Then we do not know about the specific heat capacity of the solid here, then let it be that is S, but mass given there, which is of 60 grams, and change of temperature, actually initially that is at 100, because of due to that water is present, its temperature decreased to 20, that is. So, that is why here it becomes change is 100 minus 20, which is 80 degrees Celsius, that is of 80 degrees Celsius is equal to, then specific heat capacity of the water if you are taking, which is of 1 calorie per gram degree Celsius, and mass of that water given there, which is of 100 grams is given. So, 100 into change of temperature. For the case of water, actually it is initially at 18 degrees Celsius and finally it is recorded as 20 degrees Celsius, means increased is 2 degrees Celsius, that is. Then S is equal to, from this you can write 100 into 2 by 60 into 80, that is, as both the zeros get cancelled, and finally it is nothing but equal to 1 by 24. As we are taking the specific heat capacity units for the case of water is calorie per gram degree Celsius. So, finally the specific heat of the given solid, it becomes 1 by 24 into calorie per gram degree Celsius. Okay. This is the specific heat capacity of the given solid, which is 1 by 24 of calorie per gram degree Celsius. The 17th one, a 30 grams of ice cube at 0 degrees Celsius is dropped into 200 grams of water at 30 degrees Celsius. See, 30 grams of ice at 0 degrees Celsius means that is going to be the cold body, which is dropped into 200 grams of water at 30 degrees Celsius, whereas the 30 degrees Celsius of water becomes hot body, that is. When both are mixed here, actually what happens there is that ice, it is converting into water here. Then what we have to find here is calculate the final temperature of the water when the entire ice cube has melted. Means after that ice is melted, that also becomes water, and that water, and already we are taking 200 grams of water. That complete mixture of that hot water and this cold water which is coming from the ice, both are mixing, and finally we are getting one fixed final temperature, that is. Here given that cold body which is ice given at 30 grams there, which is of 0 degrees Celsius is given there. 30 grams of ice at 0 degrees Celsius. Okay. Now, as it is of ice there, when supplied water here, then which is of hot water you are taking, that water temperature is given there, which is we are considering that as hot water, that is, and that hot water temperature it is given at 30 degrees Celsius, that is, which is of 200 grams of water at 30 degrees Celsius is given there. Okay, that is acting like a hot body, and ice, it is acting like a cold body here. When hot body and cold body both are mixed, both are coming to one final temperature here. Let it be that final temperature is T, that is. Okay, but if you see, when in case of that ice, if you supply heat energy to that at its melting point, which is 0 degrees Celsius, it starts melting and it becomes water, which is change of state takes place. But this change of state takes place, we already know that only at a constant temperature. That is why during the melting here, there is no change of state takes place, and only we are having the latent heat of capacity is coming there, which is m into L. Once the ice completely melts and it starts here converting into water, that water, if you supply again the heat energy, slowly it starts raising its temperature, that is, which is ml plus, as there is a change of temperature takes place, we have to take Sm delta T also. Okay. Then whatever the heat energy it is gained by the cold body ice, that is equal to the amount of heat energy lost by the hot body here. That hot body is nothing but the water. Whenever the water loses its heat energy here, gradually its temperature decreases. So that is why here it becomes Sm delta T. This is for the case of water, which is the hot body. Then mass of that ice, which is of 30 grams is given there, and latent heat of fusion, which is 80 calories, plus specific heat of after converting into water, which is 1, and mass is 30 grams of ice gives 30 grams of water, and change of temperature initial, that is 0, finally it is becoming T, that is. So that is why T minus 0 is the change. When come to the case of a hot body here, which is water, its a specific heat, we already know that is 1 calorie per gram degree Celsius, and mass of that given, which is of 200 grams, and change of temperature for that 32 T, and it is decreasing. So that is why here the final temperature becomes 30 minus T, that is. Then if we calculate 30 into 80, which is 2400 plus 30 T is equal to 200 into 30, which is of 6000, okay, minus 200 T, that is. Okay. Then as we want that T here, bring that 200 T this side, then 200 T minus becomes plus 30 T is equal to 6000 minus 2400, that is, which is of 230 T is equal to 6000 minus 24, which is 3600, that is. Okay. Then final temperature T is equal to 3600 by 230, of which we will get 360 by 23, it is equal to 15.65 degrees Celsius approximately. Okay, 15.65 degrees Celsius. So finally the mixture becomes, which is the combination of ice plus water if you take, finally we are getting the total quantity of water you are getting is this 30 grams of ice, which is melted as water here, and that 30 grams of water plus 200 grams of water. The total quantity becomes, which is 230 grams of water. Okay, that 230 grams of water is now at 15.65 degrees Celsius is available. Okay. If you see the next one, 18th one, a metal of mass 250 grams is heated to a temperature of 65 degrees Celsius. Then after heating that, it is then placed in 50 grams of water at 20 degrees Celsius. So, this mass metal, it is of 65 degrees Celsius is taken as hot body, and the water which is of 50 grams you are taking, that is taken as cold body here, 20 degrees Celsius. The final steady temperature of water becomes 25 degrees Celsius, means when hot body and cold body both are mixed, the final temperature here it is becoming 25 degrees Celsius, that is. On neglecting the heat taken by the container here, then we have to calculate again the specific heat capacity of the metal which is dropped into that water. That is the question given there. Okay. Now, here the hot body which is the metal given there, okay, that metal which is of 250 grams is given, and its temperature is given at 250 grams at 65 degrees Celsius is given there. That is our hot body. And whereas the cold body if you are taking, which is in case of water, and that water it is given 50 grams and at temperature 20 degrees Celsius. Then after mixing is over, it is given that both are coming to one final temperature which is of 25 degrees Celsius it is coming. Means that hot body on losing its heat energy here, it coming from 65 degrees to 25 degrees Celsius, whereas cold body which is water on gaining that heat energy here, it is raising its temperature from 20 to 25 degrees Celsius, that is. Then as we know that from the principle of calorimetry here, that Q loss by the hot body is equal to Q gain by the cold body here. As Q loss is equal to Q gain, then Q is equal to Sm delta T. As there are no change of states here, only about change of temperature will take. This is for hot body, and Sm delta T for the case of water which is the cold body here. And the specific heat of that hot body which is for the case of solid, we do not know how much its value, we are going to find now. And the mass given there for that 250 grams into change of temperature here, actually initially that is at 65, now it is becoming 25, that is. So, 65 minus 25 which is 40 is equal to then S into mass of that cold body which is of given 50 grams, that is, and change of temperature here from 20 degrees Celsius to 25 degrees Celsius, that is. So, the change becomes 5 degrees Celsius, that is. Okay. Then the specific heat of hot body becomes SH is equal to 50 into 5 which is 250 by here 250 into 40, that is. Okay. As we are taking specific heat capacity of water units calorie per gram degree Celsius, the same units we can take for the case of the solid also here. So, calorie per gram degree Celsius. Then the 250 get cancelled, of which we will get 1 by 40 calorie per gram degree Celsius. As it is 1 by 4 0.25 and again one more 1 by 10 is there, then finally it becomes 0.025 calorie per gram degree Celsius. So, therefore, the specific heat capacity of the given solid which is raised to a temperature of 65 degrees Celsius there, okay, its specific heat capacity becomes 0.025 calorie per gram degree Celsius. We see one more numerical here which is the 19th one we have. Given that 10,125 joules of heat energy boils off 4.5 grams of water at 100 degrees Celsius to steam here. Actually given there 4.5 grams of water at 100 degrees Celsius, which means already water is at its boiling point here, which is of 100 degrees Celsius, that is. Okay. And as it is given that converting into steam here again at 100 degrees Celsius, we have to find here whenever during this change of state takes place from water to the steam here, then we have to find the specific latent heat of steam here. Okay. As the heat energy directly given that and mass is also there, and it is about a change of state takes place. As there is a change of state takes place here, we do not have any change in temperatures here. So, we need not to consider about the specific heat capacity here. Okay. As the amount of heat energy it is given that Q is equal to 10125 which is 10,125 joules is given, and that amount of heat energy given to the mass which is of M is equal to given 4.5 grams, that is, of water. This water actually it is at 100 degrees Celsius is given. So, the amount of heat energy supplied is 10,125 joules, and the mass there we are having 4.5 grams of water which is at 100 degrees Celsius. Now, it is becoming into steam. Okay. As mass remains the same, So 4.5 grams of steam which is at 100 degrees Celsius, that is. Okay. Then as mass is given there, we know that when there is a change of state takes place, we have to take about latent heat here, of which in this case it is about latent heat of vaporization, that is, which is conversion of a liquid to the gas. Okay. So we have to find how much is that latent heat capacity here, latent heat of vaporization, that is. As the amount of heat energy given there, which is of 10,125 joules, is equal to mass given there, which is 4.5 grams, okay, into latent heat of vaporization, that we have to find here. Okay. Then from this we can write the latent heat of vaporization is equal to 10125 joules by 4.5 grams, that is. Okay. So 10,125 by 4.5, which is equal to, here we can write that as 101,250 by 45, that is. And finally, the latent heat of vaporization, from this if you calculate, you will get 2250 joule per gram, that is. Okay. Now actually this is in terms of joule per gram we have, but if you want to convert that into calories here, then we know that 1 calorie is equal to 4.2 joules here, but we are having 2250 joules are there. So that is why we have to take, from this we can write 1 joule is equal to 1 by 4.2 calories, that is. Then if you take this 2250 joule per gram, then finally the latent heat of vaporization becomes LV is equal to 2250 and each joule, that is equal to 1 by 4.2 calories, and we are taking for each gram, that is. So 2250 by 4.2, which means 2250, take one more 0 by 42, that is these many calorie per grams, that is. If you calculate that value here, we will get approximate 535.7 calorie per gram, that is, it is approximately equal to our 540 calories per gram. The actual latent heat vaporization of, in case of steam, that is, which is 535.7 calorie per gram approximately we are getting. So like this we are having the number of questions they are asking in case of these MCQs. If you see multiple choice question, more number of questions they are asking about change of state, the process of change of state from one phase to another phase. Like we see in case of this condensation process, gaseous phase to the liquid phase, or in case of this case of melting case if you take, which is about solid to liquid case, or even in case of this evaporation or the boiling case, which is about conversion from the liquid state to the gaseous state here. So based on that we are having a number of MCQs we have, and in the same way if it come to the case of a numerical type of questions, if they ask means they are asking about the final temperatures after mixing the hot body with the cold body there, or hot water with the cold water there, and finding if you are having a solid mass if you are taking, when it is dropped into water there are changes of temperatures we have, finding the resultant temperatures, or finding the specific heat capacity of the given solids, or even like this in case of the mixtures we can take ice plus water mixture or water plus ice mixture, or in case of this steam and ice mixture. Like this we are having different questions they are asking.